Welcome to our workshop on high performance computing. My name is Avendaño-Franco, and on this video we will make a small introduction to high performance computing. Two main concepts in high performance computing are size and speed. Basically everything on HPC is about those two topics. Supercomputers are big machines. They could be of the size of a room. They could be as big as an entire coliseum. They also have important requirements in terms of power and cooling. Those machines can take up to 10-20 megawatts of energy, which could be like in a small town, something like that. And also they produce an immense amount of heat that need to be dissipated. So they also have special cooling systems, either moving the hot air out of the building or using more specialized infrastructures like water cooling or to dissipate the extreme amount of heat that those machines generate. And also we are talking about the speed. Those are the fastest machines for doing calculations. They outperform by far the capabilities of a normal desktop computer or even a high-end workstation. So we can think about, in another perspective in the speed, that these machines are probably the kind of computers that you will have 20 years from now. So your computer on your desktop is probably equivalent to a supercomputer from 20 years ago, or more or less. So we can see all those machines also like time machines. They give you a bit of an exposure to the future, whatever speaking. So, for example, on this image we have Summit, that is the fastest computer on US. It was the fastest computer in the world until June 2020. And this supercomputer is the size of 2 basketball courts and requires more than 100 miles of cabling. So those are big machines, and they consume like I think it's more than 10 megawatts of energy for powering those machines. So they are big. This is another one, and this probably is the most beautiful cluster or the location for a cluster in the world. Is Mare Nostrum, is in Barcelona. The cluster is built inside the church, so you can see how the church looks from outside, and inside they basically took the central building, and inside is located the cluster. So there is also a plan of how that cluster looks like, and all the cabling, all that infrastructure is there, and of course a lot of infrastructure also for the cooling and powering of this huge machine. So this is a very iconic cluster in Europe. So now let's dig a little bit deeper into speed. There is one concept that is often used when we are talking about HPC speed of a machine, and it's flops. A lot of computations in science are dealing with real numbers. So the amount of processing that you can do with a computer for real number operations, for what is called floating point operations, is called flops. It's basically a measurement of how powerful is a CPU. Of course, the CPU is always capable of dealing with integers, but the amount of integers that you process in many scientific simulations or modeling is relatively small compared with the amount of processing done by floating point numbers. So this is a number to take in account. A typical computer will have something like a few gigaflops on the machine. So there are also benchmarks. And until recently, the dominant benchmark for HPC clusters was HPL, so the LIMPAC benchmark. And the LIMPAC benchmark is heavily concentrated on dense linear algebra. And dense linear algebra was a dominant portion of all that you were doing, the biggest calculations that have been done until recently. But now we are entering an age where we are also dealing with a different kind of linear algebra with more sparse matrices. So a different set of benchmarks has been created to address and get a more balanced picture of the capabilities of those clusters. So there is also the HPCG that is concentrated on conjugate gradient calculations, that is basically a sparse matrix vector multiplication, and so basically dealing with the sparse matrices that require different techniques and different algorithms for dealing with them. And now that many of those clusters are used for artificial intelligence and deep learning, there is also one benchmark, the HPL AI, that is concentrated on dealing with that. And then there is also list tables scoring the fastest computers on Earth that are publicly available. So basically research labs and universities and those kinds of institutions. And there is the top 500 list, and you can see the link there, and the graph 500 list. So those are websites that compile and give scoring list for the fastest computers on Earth. So let's deeply look here into the distribution of clusters around the world. Right now, the clusters are basically dominated by three countries. They basically hold almost 75% of the amount of the number of clusters in the top 500 list, and also the amount of power, the computational power that those clusters are able to produce. And those are China, United States, and Japan. China is now the dominant country in terms of the number of clusters that they have on the list. And United States is still the dominant country in terms of the power, the computational power that those clusters are able to deliver. And now the fastest supercomputer in the world is in Japan. So those three countries hold 74 or 74% of all the computational power that is openly available on top 500. So let's start with some terminology here to start clarifying things for those of you who are not so familiar with those terms. So on computers, we store data or we measure the basic unit of measurement for data is the byte. Byte is basically 8 ones and zeros. So with 8 ones and zeros, you can encode all the integer numbers from 0 to 255. So, and also you can encode a single character in ASCII. So we can basically score all the characters that are used in the English language. 1 kilobyte, now it will be 1000 bytes. There are different definitions that make this slightly different. For some purposes, people do not count like 1000 bytes, but 1024 bytes. But let's stick with this more decimal progression for this discussion. So 1 kilobyte, it's around 1000 bytes. So this is the number of letters that you can find in a big paragraph of text, more or less. So something like one page of a book. A megabyte is 1000 kilobytes. So it will be something like a novel, a book of medium size. A gigabyte, if you can think about that, it could be like storing with very good quality, so in lossless FLAC format. So it's you can store in an MP3 with lower quality, but in less than 1 gigabyte. But if you want to preserve the highest quality possible from the Beethoven's Fifth Symphony, it will be something like a gigabyte, a little bit less than that, but you get the idea. So a terabyte. So most of the hard drives that you can find now on stores, they are roughly 1 terabyte. So this is the unit that probably is more familiar to you now, that you can buy one drive, or your computer came with 1 terabyte of hard drive storage. So it's 1000 gigabytes. In 1 terabyte, you can basically store all the images produced on a large hospital for 1 year. So you can see that the amount. It's basically like one video, 1 hour video, or a good quality. It will be something like sorry, a video, no, like 1000 videos actually. So a collection of videos. 1 petabyte. 1 petabyte is roughly the amount of storage that a cluster today has. It's 1000 terabytes. So basically the contents of all US academic libraries fill in that storage. So from there we have exabytes. Is basically 1/5 of the words the people have ever spoken. Zettabytes. That it's basically the amount of data stored by the GAFAM companies, so the biggest big tech companies, Google, Amazon, Facebook, Apple, and Microsoft. So they are a little bit on top of 1 zettabyte. And yottabytes, so this is the biggest unit that is officially standardized. So it's 1000 zettabytes, so it's 10 to 24 bytes. So basically you can think about the number of atoms that you can find in 4 billions of gold, 100 gram billions of gold. So that will give you an idea. Equivalent to this list of units, you can find the equivalent for moving data. So when you are moving data in networks, they are not measured by bytes. Those are measured by bits, so ones and zeros. They care about each individual 1 and 0. So they're equivalent. So when they told you the amount of bandwidth on your internet connection, you probably are told about 10 megabits per second, so or 20 or 100 megabits per second. So it will be in bits. And also, as we saw on our previous slide, the flops can also receive those units. So we basically have 1 gigaflop. So is the amount of floating point operations that the cluster is able to do, or the computer is able to perform. So in the biggest clusters today are starting reaching the point of the exaflops. Most of the clusters in the top 500 are in the range of petaflops. So that will give you an idea of the amount of processing that we are able to do today. So just to give you an idea of the fastest supercomputer in the world. So the flagship of the current fastest supercomputer is Fugaku. Fugaku is another name for the Fuji mountain on Japan. And on June 2020, it entered into the list of the fastest supercomputer on the world. So just to give you an idea of the size and power of this machine has roughly 1 million CPU cores. It's composed of almost 160,000 compute nodes. They are organized in almost like more than 500 racks. So every small block that you see on the picture is one rack, and that rack hosts roughly 400 nodes on that. So when you need to serve that, to replace, they basically open that and start replacing if a node fails, so or memory is failing. So they will open that and remove one individual node. And you can see also in the picture on the right side how that individual node looks like. So they are powered by CPUs that were created by Fujitsu. So you have those and all the cooling, and you see all this metal on top. Those are the special cooling devices trying to move all the heat out of this machine. So each individual slab here is inserted on the rack, and they basically fill 400 of those on one single rack. So the amount of the memory of those machines, if you add the individual memory of all those nodes, is basically 4.9 petabytes of total memory. And compare that with your 8 or 16 gigabytes of RAM that you have on your computer. The amount of storage on those machines is around 163 petabytes per second that this machine are able to move around. And the power consumption. So the power consumption of this machine is huge, 28 megawatts. So that is like a small town. So you pretty much have like a power plant dedicated to this machine. So those are big monsters of supercomputing today. They change year by year. They are getting faster and faster. This machine is almost twice as powerful as the second machine that was submitted, the machine that on US that I showed you a few minutes ago. So those are big machines. The cost for those machines is in $7 million. So I don't think, and they disclose typically those are sensitive information. So you can think about that like in the order of 20, 40, 50 million dollars for building this machine, not counting the amount of dollars, million dollars that cost to run those machines. So the power bill and all the people and all the infrastructure, all the costs associated for running these machines. So finally, let's get all this in perspective. Let's compare a cluster with your desktop machine or workstation, and in particular make the reference to our newest cluster for WVU, that is Thorny Flat. So you will get all those numbers in perspective. So number of nodes on your computer, you just have one node. It's your computer. So there is a laptop or a desktop machine or a workstation. You have one machine. Okay. On an HPC cluster, it is tens, hundreds, and you see on this Fugaku is thousands of nodes. So on Thorny Flat, we have around 110 nodes, compute nodes, and a few other service nodes. So that will give you an idea. It's 100 times in the number of nodes compared with your computer. The total RAM on per node, so I will be counting per node. On your machine, you probably have 4, if the computer is relatively old, maybe 8. And if you are using a workstation, you probably have 24, 32 gigabytes of RAM, of memory for your computer. On the contrary, on an HPC cluster, this number is around 100 gigabytes of memory. So Thorny Flat, the smallest compute node in terms of RAM is 96 gigabytes, and the biggest is 768 gigabytes of memory. And the number of cores per node. So this is the number that has been growing over the last years. 20 years ago, usually computers have just one CPU, and that CPU has one core. Those core cannot become faster because we reach thermodynamic limits for them, so they will produce too much heat on that small area. So what the manufacturers do is now putting more cores, so on a biggest area, so they facilitate the energy dissipation without having to increase the clock speed. That will also increase non-linearly the power consumption and of course the heat production. So on your computer you have probably 4, 8, 16 cores. On a cluster, the numbers typically start around 16. On Thorny Flat, most of our compute nodes have 40 cores. There are some nodes with 24, but the majority of them are with 40 cores per node. Storage. Your computer has around 2 terabytes if you have a laptop and you have some like an SSD. This storage device is probably smaller but faster. And on a desktop you probably have 1 or 2 drives, so you can have easily 10 terabytes, 20 terabytes on your drives. On an HPC cluster we have like 100 terabytes or even petabytes, and the drives are not actually located on each individual node. Of course they have a small drive on each node, but all the data is centralized on a on a different machine, on a different system that is dedicated for storage. So we are on Thornyflat, we have a storage device that holds 750 terabytes of data. And GPUs. On your computer, you probably have one GPU. And that GPU is dedicated for graphics. So if you use that computer for 3D modeling or for gaming, that is where this GPU it's meant to do. So computing all the graphic processing for the machine. On an HPC cluster, we have typically several GPUs encapsulated on individual nodes. So in particular on Thornyflat, we have 3 GPUs, NVIDIA P6000 on a few nodes. So those nodes are dedicated for GPU computing. And finally, I put this on purpose, the final on the bottom, is the CPU speed. It's basically the same. There is not much different in terms of the speed between the CPUs on your computer compared with CPUs on an HPC cluster. They are roughly around 2 gigahertz. Eventually, even an HPC cluster, the CPUs, the cores there, are probably slower. And the reason for that is that as you put more cores on an individual socket, of course, they will produce more heat, consume more energy, and a way of balancing that is reducing the clock speed a little bit. So it is good to know that for certain things, if you are working just serially, so you're able just to use one core, your computer could be probably as fast as one individual core on an HPC cluster. But that's not the point. The point is that on an HPC cluster, you have all those nodes interconnected through a very special and expensive network, cabling and switches and infrastructure in general, that allow them to work together for solving problems. So it's not the power of one individual core, is the fact that you have nodes with tens of cores and hundreds or tens of compute nodes working together for solving demanding numerical operation of simulations, modeling, computations. So that's the whole purpose of an HPC cluster. So I hope in this short video I give you a description of the basic terminology around HPC. We will use some of this in our next videos. So it's important for you to familiarize with these concepts. Again, size and speed. Those are the key words in the HPC world, and I hope you got those ideas from this video. Thank you very much. We will see you on our next video. Bye bye.